In this video, we're going to look at a proof of Wedderburn's theorem on finite integral domains. The first thing is we need to obviously state the theorem. We're going to let D be a finite integral domain. And what that means is that D is a commutative ring with identity that has no zero divisors and a finite number of elements. And Wedderburn's theorem says that then it turns out that D is a full-fledged field. So how are we going to go about proving this? Well, the first thing is I kind of want to set up some things that just to make it clear what we know in terms of what's going on. D is finite, means that I can write D as a set that starts off with a D1 and a D2 and it goes up to some number that's going to be called Dn, and one of these guys has got to be 1 and one of these guys has got to be 0. It turns out that there is some convenience in letting D1 be the multiplicative identity for our domain and letting the last guy on the list be the 0 element inside our domain. The second thing is that we know that D is a commutative ring. And what that means is that if A and B happen to be inside D, so A and B are somebody on that list, then A times B and B times A are the same thing. We also know that there are no zero divisors. So because D is a domain, we know that D has no zero divisors. And what does that mean? Well, that says that if I know that A is not 0 and B is not 0, then I also know that A times B cannot be equal to 0. Now, the only thing that we don't know, and let's go ahead and get that here, is what we don't know is we don't know about multiplicative inverses. And in order to go from an integral domain to a field, we have to answer the question about, does everybody inside this set, not including the 0 element inside the domain, does everybody here have a multiplicative inverse? Now, there's more than one way of doing this, but we're going to basically take the same approach that our author takes in the book. And so what we're going to do is we're going to make use of the fact that we can say the following thing. We're going to first of all define a set, simply because I don't want to keep writing the set out all of the time. D star is going to be D1, D2 down through Dn minus 1. In other words, this is D take away the 0. So D star is the non-zero elements of D. And that's really just a standard piece of notation in ring theory, is that when you stick a star on top of a name, you throw away 0. Now, what we're going to do is we're going to let A be any non-zero element of D, which means A is going to be in D star. And I want to pick an arbitrary element, so I'm going to stress that this is arbitrary. And our goal is to find a multiplicative inverse element for this particular A. So what I'm going to do is I'm actually going to define a map. We're going to define a function And the author calls the function's name lambda. So we're going to take this function lambda, and his domain is going to be d star, and he's going to send the elements of d star back to d star. And we're going to define this function by saying that lambda of any d is simply equal to a times d for all of the d's inside d star. Now, this is a function from d star to d star because I want to note that a times d cannot be equal to 0, since we know a is not equal to 0, and we know d is not equal to 0, and we know this second fact because d belongs to d star. And we know this fact here for the similar reason. We know that a belongs to d star. Now, this says, so this stuff here says a times d is indeed inside d star, so lambda does indeed take d star into d star. Now, the neat thing about this lambda function is that we can show that lambda is 1 to 1, and we do this in the standard basic way that you always show that a function is 1 to 1. We're going to assume that a lambda of, say, let's call it lambda of di is equal to lambda of dj, where di and dj are two of those elements of d star, and we need to show that di and dj are one and the same unit. If we can do this, then we know that lambda is 1 to 1. So let's look at this. Since lambda of di is equal to lambda of dj, that tells us that a times di is equal to a times dj, and this is inside our domain. And we know that because there are no zero divisors in a domain, that we have left and right cancellation laws, so these a's are gone, and hence we do know that di is equal to dj, and that says lambda is indeed 1 to 1. Now, the importance about lambda being 1 to 1 is the fact that d star is a finite set. So since lambda is taking d star into d star and d star is finite, that's enough to say lambda is 1 to 1 happens if and only if lambda is onto. And that's the fact that we really actually need. So the fact that lambda is onto, and the fact that the multiplicative identity for our domain lives inside d star, those two things say there exists somebody inside d star such that lambda of that somebody is indeed equal to the element 1d. And so that says a times d is equal to 1. And that's halfway there. That's half of what we need in order to have a multiplicative inverse. And the final thing that we want to do is we want to note that since D is an integral domain, not just any kind of a domain, but an integral domain, we know that star is commutative. In our domain D. And so what does that say? That says AD and DA are both the same thing. And of course, AD, we just got done, that's actually equal to 1. So that says dA is equal to 1, and that means A inverse is indeed this D guy. And since A was chosen to be arbitrary, everybody inside the set D actually has multiplicative inverse. Let me actually write that down before saying that we've got the end of the proof. So let's finish this off with a proper conclusion. Since A was chosen as an arbitrary element of D star, we know every element in D star has a multiplicative inverse, and that's enough to say every non-zero element of D has a multiplicative inverse, and that together with the fact that D is an integral domain says D is a field. And of course D is a finite set, so D is a finite field. And that definitely ends the proof.